Hello, this is your instructor Kumaran here. Continuing on the data science lifecycle, the third phase is analytics, where you're trying to learn from the data and do your predictions. The first step in analysis is what is called exploratory data analysis, or EDA in its short form, a very famous short form in data science. What you're going to do in EDA is you want to understand individual attribute patterns. Like you take an age as an attribute. You want to understand things like the range, minimum values, maximum values, the frequency distribution, mean, things like that. The next thing you want to do is understand relationship between the attributes, like what is the relationship between age and your buying pattern, the relationship between income and gender, things like that. How does one change in one affect the other? In other words, you're learning all about relationships in this phase. You're trying to do some graphs, trying to do some analysis and understand more about what you see in the data. You then do reasoning. Is the behavior explainable? Whatever relationships and patterns you're seeing in the data, is there an explanation for why it is so? If it is not, if you don't find an explanation, then possibly there is a possibility of an error, or maybe it's a new pattern. That's something you want to discuss and then figure out. You want to look at outliers and then decide what you want to do with them. You want to either include them or exclude them. It depends upon what that outlier value is, and it's a use case by use case basis. You decide on what you want to do with outliers. Possible errors in processing you can only find with exploratory data analysis. That is a very good use of the EDA process. Let's take an example again of patient weights. We just discussed a few slides back. The moment you see a weight of like 600, you immediately know that there is something wrong with it. There is a possible error. It is also what you call outliers. Suppose there are a couple of patients who are 70 and 75 years old. Everybody else is like less than 40 years old. Then maybe you want to decide and eliminate those two records with the outliers. That is one possible outlier processing you want to do. And of course, you want to understand relationship between the patient weight and the diabetes level, the cholesterol level, and the family history and stuff like that. And finally, you validate your findings with the domain experts and say, hey, this is what I am seeing in the data. Does that gel with what you already know about? Is this something new? You want to talk to them and understand how things are. The next step is inferential analysis. What you do in inferential analysis is look for signals. You look for patterns. You look for consistency in those patterns. You look for correlations. You look for reasoning. This is kind of an overlap with exploratory data analysis. This is more in-depth and more focused and more methodical that you do here in inferential analysis. Then you check and see if the patterns are consistent and reproducible. What do you mean by consistent is, do you see the same pattern month after month after month? You see that, let's say, as the weight increases, you see that cholesterol levels increase. Does it happen for your patients every month? Every month you get a new set of patients and you keep seeing the same pattern. Do you see the same pattern across, let's say, cities, across countries, across different races? All that is a part of inferential analysis. And then you do some statistical tests to see that if the findings that you see with the data set that you have, can that be extrapolated to the entire population? Like you have data from San Francisco. Can the same will the results be the same if you extrapolate it to the entire US or to the entire world, or are they going to be different? So all those tests you do as a part of inferential analysis. Again, let's take an example of patient weight versus diabetes. You do all this inferential analysis, like you might take first data from one state like California, do the analysis and then see how California compares with New York. Are the patterns the same? Then you look at races. Like look at Asian Americans. Do Asian Americans in California show the same pattern like Asian Americans in New York? Or do Asian Americans show the same pattern as African Americans versus other people? So you do all these kind of segmentation, and then you do all this profiling during the inferential analysis, and you come up with and validate all your findings during this process. Once you do inferential analysis, the next stage is modeling. This is where all your machine learning algorithms kick into play. You apply all your machine learning algorithms to build models. And what you do in model building is you typically try to build multiple models using different algorithms and different data sets. This is all the techniques that are there in machine learning. There are some techniques about how you can segment your data sets into multiple subsets and then use them to build models and test models, and then how different algorithms can be used. And this is all the domain of machine learning is all about. If you take a course in machine learning, it is this one line that has been explored through the entire course. You of course have to test your models for accuracy. Again, there are methods for how you do that in machine learning. You finally identify your best performing models. When we say best performing, we talk about accuracy, we talk about the response time and the resources used. So you have to again make some trade-offs here as to what your best performing model is all about. Let us say one model gives you 80% accuracy and it takes 1 minute to run. There is another model that gives you 85% accuracy, but it takes 1 hour to run. So which one is more important to you? Are you more hung up with the 85 versus 80, or is it okay for you to have an 80% accuracy but have a reasonable response time? So you have to look at all these three things, like the accuracy, the response time, and the resources used, the computing power that is required to build your models, and then decide what is going to be your best model. So a model that you build at the end could be as simple as a decision tree or an equation. It can be as complex as a neural network, depends on the problem and the data in question. So, but at the end of the process, you do have a model that you select based on the different algorithms and the different tryouts that you do. After you build your model, then you're going to go and do all your predictions using new data. Again, there are ways how you can test the prediction, test your models, again a part of the machine learning courses that you will see. You have to keep validating your model accuracy. So you just don't build one model, test it once and get away from it, but you're going to be trying different models, or sometimes even combination of different models, and then see which one gives you the best accuracy possible. You're going to be trying out multiple trials and variations in this process. Trial and error is again the best term you can use here. There is a lot of, that's why I call it a research project at the beginning. You're going to do a lot of research here, try out different things and see which one works best for your specific project. A response time, resource usage, all of them are critical, especially when you have to make predictions in real time. Like a website shopper has just got into your website and is browsing through your website, making clicks, and you want to predict in real time whether the shopper is going to buy or not. Those decisions have to be made like in real time, within a second, with as minimal resources as possible. So you have to pick your algorithms based on that. You have to keep measuring improvements. So as you keep working out different combinations of the prediction algorithms. So prediction algorithms have two parts. One is the model building part and second is the prediction part. So you have to look at both of them and see whether they are better at both of them. Sometimes some prediction algorithm takes more time to build model, but they may be very fast in doing the prediction part. So different things there. So again, you have to keep measuring all your algorithms, how they perform, and then keep comparing them and then see which one is the best one you want to choose. You might even have simulations. A simulation might be as simple as mathematical simulations, or you might build software that can simulate certain use cases. So simulation is used to validate whether what your suppose your algorithm is saying that in this given situation this could be the outcome. So you need a simulator that can simulate that environment It can simulate what the entities do in that environment and then see if the outcome you are predicting is what you're going to be getting. So simulations are complex piece of software. Sometimes people do build them to validate the predictions. Once you do all this model building and prediction, the last step that you do in this case is come up with a set of recommendations. What do you do here is that at the end of this project, recommendations need to be provided to project owners, okay, on what you have done, what are the algorithms to be used, and what are the expected benefits. So all of them needs to be put together in a nice presentation and presented to the project owners. And here comes the catch. A data science project might have no recommendations to make if the data set does not exhibit any exploitable patterns. We have been talking about data science all being about learning from relationships. If the data that you have do not exhibit any pattern between the outcome and any other variable, if the outcome is not predictable from the data that you have, there is nothing you can predict. It's as simple as that. That does not mean that the data science project is a failure. You can have a project which says, let's look at our customer database and see if we can predict customer churn. At the end of the project, you can come up and say, based on the data that we have, we cannot predict customer churn. Now, that doesn't mean that the data science project is a failure. The data science project will only work if the data has patterns. So it is not the fault of the data scientist if your data does not have any patterns. Of course, it's the fault of the data scientist if the data has patterns and the data scientist fails to find them. But the data does not have any patterns. It is not the fault of the data scientist. So this is another important thing to note. Sometimes unexpected patterns are discovered that might lead to other benefits. So you might be looking at the data with a specific goal in mind, like you're looking at to predict customer churn. But you might see that, okay, I see some nice patterns. These patterns might be used to predict something else, like you might be using those data to predict upsells, for example. So a data science project might have these side shoots or side benefits. So you might say, okay, I see this nice pattern here. Maybe we got to dig in deeper. Then you go create another data science project for that and then continue down that path. So a data science project might also come up with these side benefits. In fact, a lot of them can come up during the process as you start looking at the data. And of course, you finally make a presentation on the recommendations to the stakeholders. The last one of the things you want to take note here is the iterations that are required. Even though the steps are listed here, they are supposed to be done in sequence. You do keep going back and forth between those steps. And that might be based on intermediate or at the end analysis and feedback. And so after you do all your analysis, you share it with the domain expert, you share it with the other project stakeholders. They might come back with some feedback that might force you to go back and then redo the analysis based on new light that has been shed on the data that you have. So people might have different objectives, different perspectives that might give you new triggers to go back and look at the data. That is a common thing in data science. The project team that way responds to the findings in the data, and then it can take even multiple analysis paths if you have to. Then comes the final phase, that is the production phase or the productionizing phase, which is to implement continuous processes that utilizes all the work that you have done in the earlier phases and start doing something on a continuous basis here. So here comes what is called building data products. So what is a data product? A data product is an application that works on data, gets something out of data and uses it to achieve some objective. As simple as that. What's a data product? So once data modeling and prediction algorithms are firmed up, you know exactly what you have to do. Then you build a data product. So what is a data product is basically productionizing, making the code. The code is no more, running from an IDE kind of thing. You make a code that is production quality with all the error checking in place, with all the management and monitoring in place. That will do all the steps that we have talked about, all the data engineering steps, So you have to first automate getting data feeds from all your data sources, and then you have to automate these applications to run regularly, look at the data that is coming in, and it starts cleaning up the data, transforming the data, persisting the data. Then all your analysis code will kick in, and they will start looking at the data regularly and start building models. So all of them are data products in one word. They have to be running continuously, regularly, and keep producing, keep getting data and producing these models. And of course, the prediction part of it runs real time, batch mode, whatever way it has to run. And that again is another data product that runs regularly, uses the model that has been built to make prediction when and wherever it is required. So building data science products is the final part. That is more like, this is where it's more like software engineering. This is more like software project, actually, if you want to say, because you know exactly the requirements that are there, and all you have to do is convert them into a software product. This one needs to have quality software rigor in both development and testing. And it can be deployed in enterprise and cloud models, depends upon what your data product is supposed to do. Of course, the most important thing here is also that you need to get operationalized data feeds. The data feeds from all the data sources, now they have to be continuous. When I say continuous, it's either instantaneous, you keep getting them as they happen. Sometimes you're getting these daily data dumps. Sometimes, once a week, 15-minute interval, 30-minute interval, depends on your use case. But it has to be operationalized so that the data keeps coming regularly. You don't have to work with somebody every day to get the data. It's all automated here. And of course, as we talked about it, data products perform all the cleansing, transformation, and error reporting. Error reporting is a key thing you want to be doing here. And finally, pruning of old data might be necessary. As you keep accumulating data, there's going to be a lot of data, especially once you transform the data to the form you want. All the raw data, you might want to keep them for 10 days, 15 days, and then prune them out. So that completes all the steps that you have to do in a typical data science project. But there is always something called continuous improvement. Once you deploy a data product, there are always changes in the business environment that might affect all your learning and prediction. So this is something to remember. Everything that you built as a data product, algorithms, the models, their accuracy might go down because of changes in business environment. So the learning and prediction step has to be reevaluated periodically at approximate intervals to make sure they are continuing to show the accuracy levels they originally were meant to have. And revalidation need to happen when the business process change. There is you're changing something in the business process. The way the entities behave is changing. The way the environment in which it is going to work is changing. So obviously, you have to revalidate everything you're doing here. So that might have to be another child project that is like a maintenance project or an improvement project that has to come up periodically to validate what you have been doing is all fine. Efforts to generate better models should be ongoing. This is an important thing. You just can't do it once and stop there. It has to be continuous. So in summary, for what we have seen so far, data science projects follow a life cycle. Data science projects are research type projects. There is a lot of experimentation and sometimes no end result. So that's why we keep calling it's a research type project. Signal in the data drives results, not the algorithms. Data is more important than the algorithms themselves. Multiple iterations might be necessary before reasonable results are achieved. This is another thing you want to remember. So these are the various stages in a data science project where are things that are done or should be done. So I hope this has been helpful to you. Thank you for your listening.